Hello everyone, this is Professor Iris Miano giving you your Day 7 lecture video for Math 32 at Santa Monica College. Here we will be discussing these two sections, 3.4 and 3.5, on angles and their relationships, and also you're going to get to see your very first table proofs. So that'll be very exciting in section 3.5. And here we go. Let's go ahead and start by defining several different types of angles. A lot of these are going to be terribly familiar to you, but let's make sure that we define them clearly nonetheless. Okay, let's starting with an acute angle. Here's a very generic acute angle that I've drawn here, angle 1, and it's defined as an angle measuring less than 90 degrees. Any angle measuring 90 degrees is therefore, by definition, an acute angle, and aren't they adorable? Sorry, I have to throw in that joke. It's pretty much mandatory in the math department. Okay, moving on to right angles. We already introduced this one. These are angles that measure exactly 90 degrees as depicted here in angle 2. Obtuse angles are angles that measure more than 90 degrees but less than 180, not including those endpoint degree measurements. Somewhere strictly between is going to be excuse me, the measurement of any obtuse angle. And then a straight angle, as has already been formally defined in this course, measures exactly 180 degrees as seen here in angle 4. And then lastly, we have a reflex angle, which is kind of like the outer portion of an acute angle. Basically, it's an angle measuring more than 180 degrees but less than 360, as indicated here with angle 5 being the outer, the exterior angle, so to speak, rather than the interior, which in this case would be going back to the acute angle definition. Okay, moving on. Here's some more important terms that we need to define. What does it mean for angles to be adjacent? Well, what do you already know about the word adjacent in your, English language education? You know that adjacent things are next to each other, and that's definitely true about this term adjacent angles. These are two angles specifically in this context that share a vertex and a side. So in the figure below, notice that excuse me, angle PSQ is adjacent to angle RSQ simply because they share a vertex S and a ray SQ, which is one possible side type that adjacent angles could share. They could be sharing a line segment or a line for that matter. Just has to be a side of some sort. Okay, congruent angles. We probably have a pretty good idea of what this is already, but we're going to formally define this term here in saying that congruent angles are angles that have the same measure. In fact, this was the very first definition example that we entertained when we were first deciding what criteria needed to be met in order for a definition to be a good definition for a term, if you recall. What is an angle bisector? Well, that'll be a ray which cuts an angle exactly in half. So we could use the same exact figure here as well in order to define angle bisector, in which ray DB is acting as an angle bisector. So we would say that it bisects, in this case specifically, angle ADC. And I want to bring up something a little bit off topic before we get into complementary and supplementary angles. You would not, in this case, name this angle right here angle D, right? You have to be a little bit more specific here because there's more than one possible angle being named that shares this vertex D. So you have to really use the three-letter name at the very least in regard to naming the angle that you're referring to. So if you want the collective angle here, the 70-degree angle, you would have to name it angle ADC or angle CDA. Saying angle D is not enough information because there's also interior angles according to angle ADC, namely angle BDC, excuse me, or angle CDB, if you want to name it in the opposite direction, naming the vertices and points on the angle, Or there's also angle ADB or BDA. So anyway, when there are more than one angle in play that share a vertex, you really have to rely on the three-letter naming in order to specify which angle you're referring to, just as a rule of thumb. Okay, moving on to complementary angles. What are complementary angles? These are angles that have a collective measure of exactly 90 degrees. So when you add up their measurements, they sum to 90 degrees. Now, notice in the figure that angles 1 and 2, which are defined as complementary by virtue of meeting the criterion of the definition, happen to be adjacent to each other, but that's not to say that complementary angles need to be adjacent or sharing a vertex to one another. They simply have to have their collective measure sum to 90 degrees. The same is true for supplementary angles, just change the degree measurement. These are angles that have a collective measurement of 180 degrees, so when you sum their measurements, they equal 180 degrees. And in the figure, again, I'm showing these supplementary angles, X, Y, W, and Z, Y, W, as being adjacent to each other, but they need not be to fit the definition of this term. All right, moving on. Let us define vertical angles here. Vertical angles are non-adjacent angles, so not sharing a side and a vertex, in opposite positions that are formed when two lines intersect. So, looking at lines M and P in the figure here, what are the two pairs of vertical angles that you see? They are angles 3 and 1 are vertical because they're non-adjacent in opposite positions that are formed when two lines intersect. So angles 1 and 3 certainly fit that definition. Furthermore, angles 2 and 4 are also vertical angles to one another. Now you could probably look at this and be like, I'll bet there's something true about vertical angles in regard to their relative measures and therefore congruency, in which case you are definitely on the right track in uncovering a very soon-to-be revealed theorem. So stay tuned for that. Okay, postulate 8. It states, and remember, postulates are theorem-like statements that do not need to be proven. Excuse me. Sorry. I'm going to use a cough drop over here. I almost feel like I might go downstairs and go grab one in a minute. Maybe before I make the next lecture video. Postulate 8 states that the measure of an angle is a unique positive number. Doesn't this sound very familiar? Didn't we have a postulate that was presented in the previous section about line segments having a unique positive number as their measure? Yes, that is very true. So, this is kind of like the ruler postulate, if you recall. This one could be called the protractor postulate, but it doesn't have that name. I feel like that's an opportunity lost. So if you were to, going back a couple of clicks, take a generic angle ABC as shown here and use a protractor in order to measure its degree measurement, you would want to line up the cipher, the central area here, with the vertex of the angle, and have the horizontal edge or some appropriate edge line up with the 0 measurement. And notice that the top measurements in black start at 180, so you definitely want to read the blue smaller measurements underneath in order to find the correct measurement. And we notice that the blues go all the way up to 50 before I find the edge where it's lined up with the this other ray. And then we go, 1, 2, 3, 4-ish, almost like 54 degrees. And, we're just estimating here. So I'd say it's pretty good to say that the measure of angle ABC in this case is 54 degrees, and it can't be any other measurement, right? Unless, of course, we're going to use a totally different measuring device with different units. You would just say it's 54 degrees, it's uniquely that measure, and you're not going to say it's also like 27 degrees or something absurd like that. Okay? Great. Postulate 9. This one's got a name to it, angle addition postulate. And so we will definitely be using this one a lot in the future, along with the segment addition postulate that was presented in the previous section. Anyway, this postulate states that if a point D lies on the interior of an angle ABC, and these are just generic names for these things, I'm going to present a figure for you in order to illustrate this postulate, then the measure of angle ABD and the measure of angle DBC equals the measure of angle ABC. So it's kind of just showing how if you throw a point inside the interior of some angle and connect the vertex of that angle to that point ray style, then two angles are going to be formed and their collective measure is going to be equal to the measure of what we would call the main angle, in this case angle ABC. So notice how this equation here is illustrated by this figure and by virtue of having these two adjacent angles that are formed with the incorporation of this ray, the ray being a connection between the vertex of the original angle and some point in the interior, and that means by virtue of this postulate we can state that the two measures of the angles being formed with the incorporation of the ray form the collective measure of the original main angle. Okay, cool. Here we go. Moving on. Here's our very first theorem in this section. So you'll notice that the numberings for the theorems are pretty systematic, right? So the first two numbers in the theorem name is always denoting what section it comes from, and then the third number is the order in which the theorem's presented. So this is the first theorem in section 3.4. Not that we necessarily want to memorize the theorems this way. In fact, I emphatically ask that you do not do that, that you get to know these theorems by their content. So more or less memorize them. I hate to use that word though. I would prefer that you think of the way that you want to get to know these theorems as internalizing them. And however you decide is best for you in order to do that, according to your learning style, I'm going to support you. And if you have any trouble figuring out what a good way for you to learn these theorems is, we can discuss methodology for sure on that regard. But that's neither here nor there. Let's just go ahead and read this first theorem. It states there is one and only one bisector for an angle. So this is kind of along the lines of the postulate that was stating that angle bisectors, or sorry, that measurements were, oh no, sorry, I'm trying to draw comparisons from previous postulates, but I wanted to say that this is actually the angle version, of the very first theorem that was presented in section 3.3. It was 3.3.1 theorem, and which states that there is, for every line segment, there's a unique midpoint. So this is kind of like the angle version of that. For every angle, in this case, generic angle ABC, there's a unique bisector, and it's coming in the form of this ray DB. And we can state that it's the bisector by virtue of this notation right here. Ray DB bisects angle ABC. All right. And it's only possible angle bisector, which is, saying there's one and only one. It's another way of saying it's unique, right? So you'll have this phrasing, or these theorems, authors will often use the word unique to determine to the reader that, there's no other of a certain thing. All right, let's get into our very first example in which we're given a figure. We're going to be representing some angle measures via algebraic expression or an explicitly given degree measurement here. And so I want you to note that this figure is not drawn to scale, and this is, a little bit of practice for you to give some leeway to some of the figures that are drawn in your book. They are also not necessarily drawn to scale. You don't want to assume that you could put a protractor up to this bad boy and be like, oh, I can see that technically this angle TSV is the same angle measure as angle RST. In fact, just by looking at it with the naked eye, I can see that they are not the same angle measurement. However, look at the very first given statement. It says that ray ST bisects angle RSV. RSV And if ST, this ray, is supposed to be bisecting this main angle, then that means these two angles in the interior are supposed to be the same measure as one another, right? So they are being represented in these algebraic forms as 2x plus 3y and 3x minus y plus 2, right? RST and TSV. And then angle RSV, which is the main angle, has a total measure of 80 degrees. So we can put this information together in myriad different ways in order to find the value of x and y. You're going to need to put your algebra hat on for this in order to get through this problem, because you will, one way or another, have to solve a system of equations. So I'm going to go ahead and let you maybe pause the video if you want to give this a try. And in a moment, I'm going to go ahead and show what the values for x and y are. But my hint is that you want to use what you know about angle bisectors and use that to form a system of equations. So two equations so that you could solve for the two unknowns x and y, and go for it. There's a few different ways to do it. And if you are stuck on coming up with a way to solve this system of equations, or to even come up with a system of equations, we could talk about this in class. But the answers, the values for x and y, that could come about from solving this system, there's actually other ways to do it, just so we know. We'll talk about other ways if you want to in class. They will result in x equaling 14 and y equaling 4. Okay, so anyway, hopefully that was a little bit of fun algebra review for you. And if it wasn't fun and you're like, oh my god, I don't know how to do this, please, let's talk about it in class. Okay, but let's, for the purposes of this video, go ahead and move on to the next thing, which is going to be constructions 3 and 4 on page 154. I actually do not do construction demonstrations in this video. I'm going to make a separate video for that, which I use my phone, and it's a whole nother thing. So definitely, in regard to covering this material, check out the additional video on constructions 3 and 4. But I believe we are ready to move on to section 3.4 material. We have technically, in moving past the construction demonstration yet to be viewed, we have finished what section? 3.4, and we are moving on to section 3.5 on the introduction to geometric proof. And in order to do so, we have to introduce just a gigantic pile of properties. And here are a slew of them, and we're going to, on your lecture notes, if you printed those out, I've provided a little space for you to put a generic example of each one of these properties to help illustrate it. Okay, so let's start with the subtraction property of equality. That is to say that if you have an equation, so some statement of equality, you could subtract, addition property of equality. I don't know why I said subtraction. I read the second one first. I don't know, my eyeball went there on accident. We're definitely clearly starting with addition property of equality. My apologies for the confusion. So, the addition property of equality states that if you have any statement of equality, so any equation, you can add the same thing to both sides of the equation, and the equality is maintained. Like the integrity of that equal sign is not besmirched, okay? Because you've added the same thing to both sides. So it's like, think about adding the same amount of weight to two sides of a scale. It's still going to be balanced. And so that's how the addition property of equality works. And the same is true as if you take away the same weight from both sides of a scale, right, and enter the subtraction property of equality. So we have a generic illustration of this in the form of a conditional statement, okay, where we've subtracted c from both sides of the original equation, a equals b. You can also, furthermore, multiply the same thing on both sides of the equation and still maintain its equality, and divide as well, as long as you don't divide by a 0. That's the only caveat that you have to add to the division property of equality. Now, we use addition property of equality, subtraction property of equality, multiplication property of equality, and division property of equality quite a bit in this class, and so it does lend itself nicely to acronyming. And I usually call these properties of equality by their acronyms APO, SPO, MPO, and DPO, respectively, for those 4 particular properties of equality. So if you ever hear me shortening them in that way, I'm referring to those particular equality properties. All right, so we have several other ones that we want to illustrate, and they have somewhat shorter illustrations associated with them. And enter, for example, the reflexive property, which I illustrate with a very simple equation of A is equal to itself. A is equal to A, which is to say that anything is equal to itself, which might sound like a real forehead slapper, like, really, why do we have to say this? I will get into some examples a little bit later on in which it becomes relevant. Basically, if you want to say, like, if some angle, for instance, if I came up with a really specific example just to kind of get you to a point where you're like, I don't see how this is even helpful. Let's say that you had one angle in a triangle that happened to be also in another triangle in the same figure. Like, it was, so it's a shared angle, but it exists in 2 separate triangles, and you wanted to eventually be able to prove that the 2 triangles are similar to each other. Well, one of the things that you'll need to do in order to prove similarity is to at least show at least one pair of angles are congruent to each other among the 2 triangles. But if this one angle exists in both triangles, then saying that it's equal to itself is a step in the process of showing that the 2 triangles are similar to each other. Okay? Anyway, that's a really specific example. We'll get into, the nuanced details of that when it becomes more relevant for us, but that's one instance in which you might care about saying that something is equal to itself. It sounds so silly, but it really actually becomes helpful. Next, we have the symmetric property, which is to say that if 2 things are equal, 2 separate things are equal, or, you could do this with A and A as well, using an extension of the reflexive property. But if you're saying that 2 things are equal, you could do so in the reverse order, and it's saying the same exact thing, okay? Still true. If A equals B, then B equals A, right? Okay, so there's another one that doesn't seem like it's incredibly helpful or relevant, but I'll show you instances in which we really are grateful to have the symmetric property. And then the distributive property is going to be something a little bit more familiar, in which you have a factor in front of either a sum or difference or a collection of sums and differences, and you're just distributing that one factor over, all of the sums and differences. So there you go, which is just to say that if you have the factors separated over the sum and differences, it's equal to distributing that factor to every single term over the quantity. Then there's also the substitution property, which we will use. You will be astonished by how often we use the substitution property. When 2 things are equal to each other, by substitution, you can replace one for the other. Okay, and this is going to be one that you use all the time. The transitive property is very much related to the substitution property, but it involves 3 separate items, whereas the substitution property involves a direct replacement one to another. The transitive property has to involve 3 things in order to work according to the definition, which is to say, if you have A equal B and then B equals C, B is kind of acting like the middleman to connect, and you can use the transitive property to connect A directly to C, coming up with this conclusionary statement right here, A equals C. Okay, this is also very much similar to what I was getting at when we were talking about that standard form of the valid argument, the law of syllogism. It was 3 conditional statements. 2 of them were involving 3 separate statement components. If you recall, it had something of the form, if P then Q as the first statement, if Q then R as the second statement, and then the conclusionary statement being, therefore, if P then R. So Q is kind of acting as the middleman, connecting P to R in that regard. So I very much liken the law of syllogism that we were talking about back in the arguments section, section 2.4 of the textbook, to what's happening here with the transitive property. Three things are involved. There's a middleman connecting a first mentioned thing to a last mentioned thing. Alrighty, so let's move on to some examples. And the first ones are, I think they're kind of straightforward, but at the same time, the wording might be a little bit challenging. So I want to make sure we go through at least a couple of examples together in this lecture video, in which we are asked to determine which property justifies the conclusion of the statement, the conclusion being the consequent, right? The x equals 17. So we are presented first with the antecedent. If x minus 5 equals 12, then it must be true that x equals 17. Well, how do you get from here to here? Like, what needs to happen in order for this equation to turn into this one? Well, if you are up to snuff on your algebra skills, you may notice that you can add 5 to both sides in order to get this conclusionary statement, and so we are therefore using the addition property of equality, or APOE, APO for short, if you're, looking for some more brevity. Okay, cool. So that's what they intended you to do for that exercise. For this next exercise, it might, it's kind of so easy it's hard, and I wanted to make sure that you understood what the purpose of this next exercise is. The instructions are to state the property or definition that justifies the conclusion, the then clause, right? They specify this in case you didn't know where the conclusion is in a conditional statement. Okay, given that the measure of angle 3 plus the measure of angle 4 equals 180 degrees, then angles 3 and 4 are supplementary. So it's like, what are they asking for here? I don't know. When I first read this, I was like, wait, what? What am I supposed to be doing with this exercise? So they want you to state the property or definition that justifies calling these angles supplementary. Well, you're using the definition of supplementary angles. Duh. Right? This is what I mean by it's so easy it's hard. You're just like, oh yeah, well, okay, well, obviously they're doing that, but that's what you wanted us to recognize? Yes, that's all it is. We want to justify the then clause or the consequent conclusion, as they're calling it, with either a definition or a property. In this case, a definition is most appropriate, and it's the definition of supplementary angles specifically. Okay. Moving on. Next exercise, use the given information to draw a conclusion based on the stated property or definition. So we're using a property here, and here is the statement. It's a conjunction, right? Because we're using the word and here. And we have two statement components that are given. The first statement component links together through equality the fraction 1/2 to the decimal 0.5, and then the decimal 0.5 is then linked through equality to 50%. Okay, so using the transitive property of equality, what can you conclude from this? Well, we have three things in play, and the 0.5 appears to be acting as the middleman, hint, hint, hint. So it looks like we can connect 1/2, the fraction 1/2, directly to 50% using the transitive property of equality. And that is the purpose of that exercise there. So in your homework set, you'll have similar exercises to those three. And so hopefully this brief introduction to a few specific examples will help you get through those with gusto and confidence, and knowing full well what the intention of the exercises are. Okay, now let's take a look at our very first box style proof. Okay, so in looking at this very first box proof, it's an algebraic proof, so we're not in geometric proofs yet. We're going to have one more example of that before we end the lecture video here. But this gives you the structure of the geometric proofs that are yet to come, and that is to say that they're in this box with statements on the left-hand side column and reasons on the right-hand side. Sorry, left-hand side is statements, right-hand side is reasons. And this one is partially filled out. It has got the three statements that prove this given statement, and all we need to do is come up with the reasons or justifications for each of these three statements. Okay, so here I'm going to let you in on a little secret about the first statement, which happens to be the given statement, like what the justification for the first statement is. It is always simply given, okay? If it's given to you here, it's given to you there, all right? And then we need to think about how we get from the first given statement to the second statement and come up with justification for what happened from step 1 to step 2, basically. So what do you think is happening algebraically here to go from step 1 to step 2? Well, it looks like we appeared to subtract 9 from both sides in order to get this result. So I would say that we are using the subtraction property of equality, or you can shorten it up with SPOE, SPO, or SPO, you know, if you want to be hugely brief there. You do not need to say specifically that you subtracted 9 from both sides. You just need to state the property that allows you to go from one step to the next. And in this case, it was SPO, or SPO, or subtraction property of equality. Now, how did we get from the second step to the third step, which happens to be our proved statement? Well, one thing you might, through context clues, try and assume you can do is just write prove, LOL, because you got to write given for this first statement. Please do not ever do that unless it's a joke, and then say, just kidding, I meant to say division property of equality for this particular one, because from step 2 to step 3, we had to divide 2 from both sides. Or you could argue that it's illustrating multiplication property of equality, and your argument could be that you multiplied both sides by 1/2. That would be perfectly acceptable as well. So you'll find that sometimes you will have more than one correct answer for justification, but usually it's something pretty specific. Okay, and that's a proof. That's your very first table style or box style proof. It happens to be algebraic in nature. Let's go ahead and look at our very first geometric proof. Okay, just a moment. Let me check my messages. Okay. So we have a given statement. E is the midpoint of a line segment DF. We have a corresponding figure. And then we want to take a series of steps to ultimately get to our proof statement, which is that DE must be equal to 1/2 of the measure of DF. Sorry, the measure of line segment DE is what I meant to say here, because anytime you're referring to a line segment without its hat on, notationally, you are referring to the measure of it. So just to be clear, oh, okay. Just a moment here, guys. Sorry, I'm just texting my babysitter. Okay. Okay, let's, we're going to wrap this up here. So the statements are already given to you, so we're kind of still doing a lot of hand-holding in our presentation of table proofs at this time. You're still not expected to write them. Pretty soon we're going to enter into a section where I'm going to show you the steps that you would take in order to write your own geometric proofs from start to finish with only simply a theorem. And you can even, from a theorem, create your own figures, which will sometimes be the case in regard to some of the exercises that you'll be taking on. So always, the first statement is what is given. So what would be the reason that you get to propose for the first statement? Well, you get to say it's given to you, okay? That's your one freebie, basically. And the next statement, notice, is saying that the measure of line segment DE is equal to the measure of line segment EF. And what allows us to be able to state this? Well, we could justify this by using the definition of this term midpoint. Definition of a midpoint, okay? Because the definition of a midpoint is that it's a point on a line segment that that has equal measures of the line segments on either side. There's a couple of different ways that you could phrase the definition of a midpoint. If you are confident that you are using the right term, it's okay to just write definition of and the term. But if you are ever kind of in question that the term that you're using is not a correct definition, or not the correct word to use to justify a certain statement, the best rule of thumb is to write out the definition itself. Furthermore, moving on to statement 3, notice that we have DE plus EF equaling DF, okay? And at this point, it might not be intuitive like why you would necessarily write one step to the next, and that's okay. For our purposes, we just want to look at the partially completed proof and be able to justify each step. That's enough for us to be able to tackle at this point in our curriculum here. So how can I say that for a line segment DF in this case, that if there's an extra point inside of the line segment that creates two other line segments, that their collective measure is equal to, the sum of its parts? Well, you would be using the segment addition postulate, which has, one of those few postulates that has a name. This one has a name and we use it quite a bit. Okay, then notice that we're stepping out into statement 4, in which, statement 4 looks really familiar. Isn't that almost the same as statement 3? What's the difference between statement 3 and statement 4? Oh, well, notice that the second term on the left-hand side of the equation got replaced. EF turned into DE. Well, is that okay to do? Well, yeah, because in statement 2, it was said that they were equal, so we can use a substitution or use the substitution property in order to make this statement happen. Okay. Now, the next one is kind of a little bit strange. The answer in the back of the book associated with a proof similar to this one had a different justification than what I'm about to give, but I wanted to present this as an okay justification as well. So what do you think of when you look at DE plus DE and then see that it gets simplified to two DEs, two measure of length line segment DEs? It looks like you're what? Combining like terms? If you were thinking that, then I would say that that's excellent justification for what happened in statement 5, leading up from statement 4's presentation. So if you are looking at this and you're like, okay, well, what did the back of the book say? The back of the book said that this was substitution, and I just thought that was a little bit of a leap because it wasn't presented explicitly earlier in the proof that these two things were equal to each other. We know from common knowledge of our algebraic, skill set that this is true, but I felt like that was a little bit weird. But combining like terms seemed like an okay justification for me, so I wanted to present that as an option if you see something like this again. Okay, now let's go to justifying the very last statement, which is our proof statement, which we know as long as we can justify this last statement, we have completed our proof. And please do not put prove down here. That is not ever justification for the last statement. So how did we go from statement 5 to statement 6? It looks like we either, multiplied or divided by 2 on both sides, or we multiplied both sides by 1/2. Either one will do as justification. It looks like when I was writing this up, I went for depot. Oh, sorry, let me go ahead and go back to this for just a moment. And this is a a complete proof of the following given and proved statements, which could be rewritten as a conditional statement in the form of a theorem. We'll get into that a little bit deeper. I think in section 3.7 is where we get into the formal proof of the theorem. And that's it for now. So here are the 2 homework sets that I recommend that you tackle, preferably before we meet. Again, but we could also I could entertain the idea of doing a couple of problems from this homework set in the class session proper. It's just whatever you want to talk about. That's it for now. Thank you so much for your attention. Bye bye.